Okay, question number 2. This question is taken from 2003 May paper. Though there's a old paper, but still, the questions in IB old papers are really good enough. Okay, it gives you into detail. You can solve this problem. Now, state what is meant by an ideal gas. What is an ideal gas? Ideal gas means the first thing that you can say here is that there is no intermolecular forces between the molecules. That means what? The molecules do not stick to each other. Okay, that's what you can say. You can also write something like, okay, so the second point you can write is maybe molecules are considered as hard spheres. You can write this. Then you can also write obey PV is equal to nRT, ideal gas equation. You can write this over here. And then you can also write, if you want, it moves with random speeds. Okay. And okay, so all this you can write. Yeah, so all these 4 points are sufficient. In fact, you need only 2 points. Okay, next. The internal volume of a gas cylinder is 2 into 10 power minus 2 meter cube. Volume is given. You put a gas inside it, it will fill up the same volume. The ideal gas is pumped into cylinder until the pressure becomes 20 megapascals. Pressure is given. Temperature is given. Determine the number of moles of the gas in the cylinder. So what do you do? So this is related to PV equal to nRT. So we will have PV is equal to nRT. What is it we required over here? P is known, V is known, T is known, R is already known, gas constant. It should be there from your data booklet also. Get the value of N. N should be equal to PV divided by RT, which should be, now substitute all the values. So 20 megapascals. Many students make a mistake over here. Instead of mega, they just write 20. That is wrong. Okay. So 20 multiplied by mega is 10 power 6, multiplied by volume. What is volume? Volume is 2 into 10 power minus 2. See, check that everything is in SI unit. SI unit over here, and divided by R. What is R value? 8.314 or 8.3 multiplied by T. See, don't substitute this value. Whenever you are doing problems in thermal physics, see to it that you are doing everything in terms of Kelvin, SI units only. Okay. Temperature should be in Kelvin until unless it's a delta T value. If it is temperature in thermal physics, it should be in Kelvin. So therefore, now what we do is we convert this one. This should be 273 plus 17, which should be equal to 290 Kelvin. 290. Now let us substitute all this and get the answer. So it should be 20 into 2 is equal to 40 divided by 8.3 is equal to so much divided by 290 is equal to 0.0166. I write down this first. 0.016 multiplied by, there's a 10 power 6, there's a 10 power minus 2 here. This becomes 10 power 4. So now how much can we write this here? This will be, okay, 166 you got, right? Okay. So this will be 1, 2, 3, 4, which will be 166. What is this? N. N is number of moles. 166 moles, or you should get an answer nearly 170 moles if I round it up. Okay. Calculate the number of gas atoms in the cylinder. Now how do we do this? So for this, what we do is, we know that number of moles is equal to number of atoms divided by Avogadro number. N by Na is equal to N. So what is that you require? You require the value of N. Na is the Avogadro number. So we'll write N is equal to N times Na, which should now be 170 multiplied by, what is Na? 6.023 into 10 to the power of 23. So if I do this, how much will this be? So I got, I'm sorry, I'll make this 166 because it's approximation. We will use the actual value 166. So I will use 166 multiplied by 6.023. I get the answer as 999.818. 999.8 multiplied by 10 power 23, which is nearly, I can consider this 1000. 1000 into 10 power 23, which is nearly equal to 10 to the power of 26. What is this now? This is your number of molecules. Practice it in such a way that you always write the units alongside your equations or your numbers. Okay, otherwise you will not enjoy physics with it. Then, using your answers in B, determine the average volume occupied by one gas atom. Okay, now you have got the total number of molecules. You need to find out the average volume occupied by one gas atom. What does it tell you? It means you are supposed to calculate what is the volume per molecule. Now we know that the total volume of the gas container is equal to how much? Total volume of the gas container we have substituted 2 into 10 power minus 2. Okay, this is 2 into 10 to the power of minus 2 divided by how many molecules did we got? 10 power 26. 10 power 26. Of course, you can use 999.8 also, but you know, then you say about the number of molecules, it should be a whole number. Can we have 0.8 molecule? We cannot have 0.8 molecule. That's the reason I did not change this, or I did not change it over here. Okay, I took it as 1000 directly. Okay, so therefore I get this value. So 2 into 10 power minus 2 divided by 10 power 26, which will be 2 into 10 to the power of 28. What is this now? Volume per molecule. This is 28. 10 power minus 2, 10 power minus 28. Meter cube per molecule. Meter cube per molecule. Okay, put this also. Then estimate a value for the average separation of the gas atoms. Average separation. Okay, let me assume that the molecular volume, okay, is proportional to A. Okay, the separation between two atoms. In that case, because it is an estimate over here. Estimate means you can assume. Okay, so therefore A cube is equal to 2 into 10 to the power of, what's the value we got? 10 to the power of minus 28. Minus 28. So A should be equal to cube root of 2 into 10 to the power of minus 28. For the sake of convenience, what I will do is, I will write this as cube root of 0.2 into 10 power minus 27. Now we know 10 power minus 27 means cube root of it will be 10 power minus 9. Okay, so I will write this 10 power minus 9, this multiplied by 0.2 whole to the power of 1 by 2. Now it's easy for me to calculate this value. Okay, now what I will do is I'll cancel this 0.2 to the power of, do we have a cube root here? I don't have it here. Cube root 10 power x power y to the power of 1 by 3. 1 by 3 is 0.333333. When I do this, I get the answer 0.584. Get the answer as 0.584 into 10 power minus 9. What is this here? Value of the average separation of the gas atoms. So this will be meter. Okay, so this will be 0.6, 10 power minus 9 nanometer. Okay, I can say the average separation of the gas atoms could be around 0.6 nanometer. Then, okay, so with this we come to an end for this particular problem. We will see the next problem the next week. Thank you.